See? All right. So in general, I mean, this is the content. This is kind of the water tank is here. Some irregular shape. We have no idea how this one looks like. It's just general discussion. Think about I have this the potato with a rod and cross section, right? That kind of discussion. So let's say that there's a water was here. This amount of water is in there. And think about, pumping up this water, and that's the calculation we're about. How much work is required to pump up this water that is inside this tank? That's the problem. Okay, so here's the idea. How is this how they analyze it? First of all, I'm going to do this orientation by from 0 here and all the way up to the x equals h. So h seems like height of this container. Make sense? Yeah. And first thing we do is that we're gonna pump up the water a little bit. Let's say there's a little bucket, just about this size of the bucket. You go ahead and pump up the water and pull up to the top of the tank. All right. So suppose you did a lot of that somewhere down there. You were in this situation. For example, we're down here. Can you imagine? You are somewhere down there. All right. You have to pump up the line. So you're about to pump up another bucket, small bucket of water out of this. So if I take out a small bucket of water in there, this is like real reservoir size of a tank compared to the little bucket I have there. So can you imagine that will be very, very small. Thin height is decreased by, you probably don't see it at all, right? If it's a little bucket. It's like a little bucket from the ocean. You don't expect that, level of ocean goes down. Very, very tiny. So what would be the good notation for that tiny height? Riemann sum kind of notation? What was that notation? Delta x seems like a best notation there, right? So we go and divide this 0 to h, very tiny pieces like that, right? Each of the bucket actually gives you different height, because down there it seems like smaller water and large area of the water. If you pull out a bucket, it's very tiny, height, but let's assume that is all delta x, just a small quantity. Now, what else do we need to calculate the work? Suppose you put it in this little bucket and water in here. Next thing you do is just pull this one up all the way to the top of the tank, right? You pull this one up. That's where the work is calculated. We're not calculating actually like dipping it like that part. No, we're only calculating lifting part. Okay? How much work are we required to lift that? So what do you need to know to the work required to pull this one all the way up to this h? Think about it. Work calculation, right? For that bucket of water, the force that you're dealing with to lift it all the way to the top, is it constant or changing like a spring mass system? The answer is gravity. The source of the force required to deal with here is gravity. Constant or not constant? Gravity is a constant, right? So the force is constant. All right. So force we require calculating the little work calculation, WK. Is that all right? Tiny amount of work, because this is very, very tiny amount of mass in there required. So it's a force that you are dealing with that spot there, right? Times the distance, dk. Is that all right? If you're all down there and up there, this dk changes, right? But I think I was wrong about something. It's this acceleration is the same. If it is the same volume, yes, it is a constant. But if over there, if you sample delta x amount, this large amount, it's the same thickness, then you can see that's lighter weight that you have to deal with, right? But acceleration, gravitation acceleration, that's the same thing. Okay, so that's how much the work is required to pull up all the way to dk. I think calculating dk is easy. Who would like to go for dk in there? Distance from that position to that. That's how far you go, right? What do you say? The whole thing is h, right? Minus this distance here. Riemann sum notation. Where are we here? Some arbitrary kth interval, right? So xk is alright. Xk. That's the coordinate from 0 to kth xk minus 1 and xk. Does that help? Yeah, so the height there, 0 to xk, that's the height. So if you subtract from capital H, that's how far you're moving along in kth stage. Good? Okay. So how about Fk? How do you calculate the force, the weight of that thing? Maybe the tiny amount of mass that bucket of water, the mass of that bucket of water, times what? Mass times what becomes a force in the gravitational field? The gravitational acceleration, right? G. And here. Make sense? So G never changes. That was the constant part actually. But mass changes because the shape is irregular. How about mass? Does anybody know how to calculate mass from the volume? That volume is something that is more available. So I think it's the density of this matter. Let's say this liquid is uniform matter, right? So you don't have to integrate on that part or anything. So the density times the volume of that water times the gravitational acceleration times h minus xk. How about that? Does that make sense? Volume of that water. Yes. Very nice. I'm going to actually sketch that is the delta mk, but that's the weight of, approximately weight of that thin layer of water, right? Does that clarify? Yeah, so that was delta mk, the small amount of water pulling up. Okay, let's go further. Rho times, well, how would you estimate the volume of this one nicely? That's the potato idea, right? Volume of that is the delta x times what? Good cross section. To calculate the volume of this whole thing, we looked at the kth slice, multiply the thickness delta x to what? Area of this section, right? Area of the section. So that would be area of the section, AX. Area changes in this arbitrary shape, right? If you cut it here, then it's just slightly different, but it's not perfect circle or anything. Make sense? So area function A changes. So what would be the good input? A of what? XK, that's the location. That's right. XK. All right. Does it look like a Riemann sum now? Delta X, usual thing. Rho is a constant of the liquid that's in, the density constant. And G is a gravitational acceleration is constant. There's a function written in terms of xk, and there's another more specific function written in terms of xk. Riemann sum? That's a Riemann sum. So let's write that and summarize here. The work required to pull that little bucket of liquid or water up to that is roughly rho times surface area in that cross-sectional area, not surface area, section area, times the height from there, h minus xk, times the delta x. Usually should put it to the side to make it more like Riemann sum, right? G. Yeah, where'd that G go? G should go in front of the constant. G times rho. Those are two constants. All right? Then what do? We add up all these things, a little bucket at a time, right? So total amount of work is roughly sum of all this k going from 1 through n of this thing, g rho surface area, right? Not surface area, it's sectional area. I keep using the wrong term. It's section area, cross-section area, times how much you go up, the distance you're moving from there, delta x. All right? So let me kind of summarize that. To understand this one, this is the section area, sectional area, lifting distance. That's a better thing to keep in mind than just the formula itself. AX, that's better. That helps you to understand the formula and apply the formula in the right way later on. Lifting distance times the sectional area. And delta x here takes care of it into a mess, and all these constants turn it into a mess, and volumes, force, things like that, right? So if you really chop it up into a thin layer of water, it's supposed to be this definite integral value, right? Gravitational force and density, mass density, and this sectional area, and h minus xk, and the dx. xk, there's no xk, just x.